In this video, we're going to go through the process of designing an amplifier together so that you can see how I do it. Designing your first amplifier, which you'll do in lab soon, can be intimidating, but I hope this example will demystify the process. Designing an amplifier is going from a set of specifications, like Rin, Rout, and AV, back to values of resistors, voltages, and currents. In the amplifier pictured here, that means we need to pick R1, R2, RC, and RE to set useful values for Vout, VE, VB, and IC, the large signal versions of those. That's 8 variables we have to pick or derive from other relationships. And because we have so many variables, designing can feel like trying to wrangle a big pile of interconnected equations. It's even trickier because lots of designs are under-constrained, so there's more than one set of values that would make them work. However, I find that if I pick a few constraints to let me pin down some values early, then we can follow the implications of those constraints through the rest of the design. Let's see an example. For convenience, I've included the Rin, Rout, and AV of this amplifier down at the bottom of this slide. Rout and AV are the standard expressions for a common emitter, and I've modified Rin to reflect our bias network falls in parallel with RPi, which is the small signal impedance seen from the base. So looking in here. We're going to start with a set of constraints, some of which are technically device properties rather than design constraints, but don't tell anyone. Here we set VCC to 10 volts, and we assume beta is 100, and say that we want Rout to be less than 2 kiloohms, R greater than 1 kiloohm, and AV equal to minus 100. We can launch from one of these constraints to a resistor value right away. Rout is just equal to RC, so we know RC has to be less than 2 kiloohms. This statement doesn't give us an exact RC value, which is a problem. Life is a lot easier if we just pick one RC value, because we can use that to specify other values. So I'm going to pick an RC value here. Specifically, I'm going to set RC equal to 2 kiloohms. It can be tempting to try to leave RC undefined by leave RC defined by an inequality, maybe in hopes of getting a mathematically perfect value for it later or giving yourself some design freedom down the line, but that will drive you crazy. There are a lot of moving variables in circuit design, and you'll do better if you just pick values for some elements for your first few designs. Trying to keep those inequalities alive longer is a pretty sophisticated design technique that's quite hard. And though it undermines my previous point a little bit, there's actually good reason to set RC to 2 kiloohms here rather than some other value. I picked RC equal to 2 kiloohms because it means I can use a smaller IC to get the gain I want, which will minimize the power consumption in the amplifier. One unspoken constraint in almost every design is that you want to minimize power consumption. It's rare that you have so much power available that you don't want to think about it and instead want to maximize something else. If we know RC, then we can find the GM we want in order to get our gain at the right value. And that in turn implies an IC value because GM is equal to IC over phi t. Finding IC is a big deal in amplifier design, and it usually cracks the rest of the design wide open. In our case, it tells us that our large signal VO, which is VCC minus IC RC, will be 7.5 volts, and that RPi, which is beta phi t over IC, is going to be 2 kiloohms. We have some freedom in picking VB and VE, which makes this next step a bit fuzzy. However, we haven't yet guaranteed that our Rin is going to work right, so it makes sense to start picking values that will help us meet the Rin constraint. Because R1 and R2 are in parallel with RPi, we need them to be bigger than Rin at minimum, and possibly significantly bigger than RPi, so that the RPi value dominates our input resistance. Further, because the parallel operator favors the minimum value that it operates on, it doesn't help to make R1 bigger or smaller than R2. So let's assume they're about the same, which will put VB at 5 volts. We know VE is a VBE on drop below VB, so it'll be at 4.3 volts. And if VE is going to be at 4.3 volts, then we can use that knowledge to pick RE, which will set IC in turn. So we write VE equals IE times RE, and remember that IE is about the same as IC, which lets us say that RE should be 3.44 kiloohms. That's a pretty specific value for a resistor, which arose because we had to take a funny number, 4.3, divided by another funny number, 1.25. So we might not be able to find a resistor of value 3.44 kiloohms lying around in lab. Which raises a lot of questions, like could I get away with a 3.3K resistor that is lying around? And in turn, how exact does IC need to be? Which further suggests, does our gain need to be right at minus 100? These are important questions you should kick back to your client. They depend a lot on the application that you are designing this amplifier for. Alternatively, you could also adjust earlier design decisions to avoid needing this weird resistor by picking a different RC. I strongly recommend partially automating your design process using a spreadsheet so you can repeat earlier steps if you find yourself asking these questions, just by rerunning calculations. Finally, we need to pick R1 and R2, and I've let them be 5 kiloohms. I double-checked that this value will meet our in constraint, and this value also means that a fairly high current of 1 milliamp passes through the bias network. That means we're pretty likely to get the base voltage that we signed up for, because the base current is 12.5 microamps, which is only 1% of the current in the bias network. So the bias network is, so the base voltage is unlikely to droop significantly because of the base current. That said, there are plenty of other choices you could have made for these resistors. For instance, bigger values would have reduced power consumption and increased Rin, at the cost of having to optimize your base voltage and your ratio of R1 to R2 more carefully. It's also possible to go through this design in the opposite direction, starting by calculating Rin, and then using that to find VE, and in turn propagating that out to RC. Puzzling out the many paths through a design and the hidden relationships that kind of underlie them is a really fun exercise and one of the things that I enjoy about this discipline. So in summary, amplifier design can be intimidating, but it's not so bad if you use constraints to pin down key values and then propagate those constraints through the rest of your circuit. And where you have freedom in your design, pick values that make your life easier. So designs are going to be under-constrained, so you're free to pick values that make it work well for you.